Let's take a minute now to look at some of the more commonly used vaccines and which type of vaccine group they belong to. For inactivated or killed vaccines, good examples are the influenza or the flu vaccine that we are recommended to get every year by October, the hepatitis A vaccine, the injectable form of the polio vaccine. Remember, there's also an oral polio vaccine. And also the rabies vaccine that I mentioned earlier that veterinarians are routinely given. Examples of live attenuated or modified live vaccines include the MMR vaccine, which is given to babies and young children. MMR stands for measles, mumps, rubella. The varicella vaccine, that's chickenpox. The rotavirus vaccine, which is sometimes given to infants. And a vaccine that we don't use anymore, thankfully, the smallpox vaccine. When I was a child, we were still giving children the smallpox vaccine as part of their routine vaccinations. But thanks to the hard work of healthcare professionals around the globe, smallpox has been eradicated from this planet. Let's hear it for vaccination programs. The messenger RNA, or just the RNA vaccines as they're called, these are the current Moderna and Pfizer versions of the SARS-CoV-2 vaccine. For the group of subunit vaccines, which are also sometimes called recombinant, polysaccharide, or conjugate vaccines, there are several of these. Remember, these vaccines are based on a piece or a part of the causative agent. There's the DTaP vaccine, the Tdap vaccine. Those are two versions of the diphtheria, tetanus, pertussis vaccine. We're not going to get into the details of how those vaccines differ from each other, but this is a vaccine that is given in different versions at different times of life. We routinely vaccinate infants and children for diphtheria, tetanus, pertussis, but we now also sometimes give adults, and especially the elderly, one of these types of DTP vaccines. The Haemophilus influenza or the Hib vaccine is a subunit vaccine. HPV falls into that category. Meningococcal vaccines, pneumococcal vaccines, the shingles vaccine, those are all subunit vaccines. One type that we didn't talk about in detail is the toxoid vaccines. All the vaccines I've been talking about so far are used to provide immunization against viral pathogens, but it is possible to protect people against bacterial pathogens with vaccination. And one of the most important and most common bacterial vaccines, or what we call toxoid vaccines, is the one that protects us from tetanus. There's also a vaccine called the TD vaccine that protects against tetanus and diphtheria again. It's the tetanus that is the toxoid part of the vaccine. And finally, good examples of the viral vector vaccines. Remember, these are the vaccines that put viral genetic material in the form of DNA into a viral vector shell. Again, there are 4 SARS-CoV-2 vaccines that fall into this category. The Ebola vaccine, which you may or may not be familiar with, also falls into the viral vector category. One of the things I haven't mentioned yet, specifically about the SARS vaccines, is this. Some people have questioned why we've gone to the trouble and the expense of developing viral vector vaccines against SARS-CoV-2 when we have such wonderful modern messenger RNA vaccines against that virus? The answer is this. The viral vector technology is tried and true. We've been using viral vector vaccines for a while now, and we know how to make them, and we know that they're safe and effective. But here's another big advantage to viral vector vaccines compared to RNA vaccines. RNA vaccines have to be kept at an extremely low temperature, about -80 centigrade Celsius, very, very cold. In comparison, a viral vector vaccine only needs to be refrigerated. So if you're trying to deal with a pandemic virus and your goal is to reach herd immunity around the globe as quickly as possible, you're going to want to develop some vaccine that does not require any special handling. Remember, there are parts of the world where it's very hard to find a -80 Celsius freezer. There are lots of them here in the United States and in other very wealthy countries, but not everybody has that available. So we need vaccines that can be kept at just normal refrigeration temperatures so that everyone around the globe has access to these life-saving vaccines. These SARS-CoV-2 vaccines have been in the news a lot lately because for some bizarre reason, there are people in our country and in other countries who just oppose the concept of vaccination. But these vaccines are now available, they are in wide use, and they are helping us achieve herd immunity here and around the globe. Hopefully, enough people will choose vaccination that herd immunity can be reached in time. The Pfizer, or BioNTech as it's sometimes called, SARS-CoV-2 vaccine is the RNA type. So is the Moderna, as we mentioned. These viral vector versions of the SARS-CoV-2 are the ones that have been made by Johnson & Johnson, by AstraZeneca, and the newest one by Novavax. Now I've put an asterisk next to the first three because those are the ones that are currently approved for emergency use here in our country. The AstraZeneca vaccine, which is a vector vaccine that uses DNA as the subunit from the virus. The AstraZeneca vaccine is available overseas right now and is in fairly wide use overseas. The Novavax vaccine is a vector vaccine that uses protein as the subunit. That one just became available, and that one is also in wide use overseas. Now, there has been some reports of side effects, damaging, dangerous side effects, particularly with Johnson & Johnson. You've probably heard about the blood clotting issue. And the RNA vaccines, you may have heard about the myocarditis or cardiac inflammation issue that sometimes arises with the RNA vaccines. It's very, very important to know that those side effects are very rare. We're talking about fewer than 1 in a million. The risk of dying from a side effect from one of the SARS-CoV-2 vaccines is much, much lower than the risk of dying from COVID-19. All of these vaccines right now are currently on emergency authorization. And what that means is, in our country anyway, the Food and Drug Administration has determined that the risk of using the vaccine is lower than the risk of being unvaccinated and contracting COVID-19. These are emergency authorizations. So the vaccines have gone through some rigorous testing, but they have not yet been fully approved. And remember, in our country, approval is based on two things: how safe and how efficacious, or how effective the vaccine is. Something else to note about these vaccines that's very important and yet never gets talked about in the media. You often hear percentages thrown around for the vaccines in terms of their effectiveness. For example, you may have heard numbers in the 90%, 90 and 94% for the Pfizer and Moderna RNA vaccines, compared to a number around 75% for the Johnson & Johnson vaccine. It's really unfortunate that these percentages were distributed by the media without explanation. The truth is, all of the vaccines are good. All of the vaccines are very effective at preventing severe disease and death from COVID-19. But these vaccines were produced by different companies, and when they were studied, the experimenters used different endpoints in their experiments. In other words, sometimes the vaccines were evaluated in terms of preventing death from COVID-19. In other experiments, vaccines were evaluated at how well they prevented admission to the ICU with COVID-19. Other endpoints were how well the vaccine prevented severe disease requiring hospitalization with COVID-19. Different endpoints for each of the studies. That means you cannot compare those numbers from one vaccine to another. You can't say, well, the Pfizer vaccine is the best vaccine because it's 94% effective. The Pfizer vaccine was evaluated differently than the Moderna and the Johnson & Johnson and all the others. They used different endpoints. That's why they generated different percentage effectiveness. All of these vaccines have been proven safe and effective at reducing the most severe disease caused by COVID-19, effective against hospitalizations and admissions to the ICU and deaths from COVID-19. All of them, regardless of the endpoint that was studied, all of them are effective at preventing the most severe consequences of COVID-19. You may have heard reports in the media of people who have been fully vaccinated who have still come down with COVID-19 and even been hospitalized and even died of COVID-19. These are referred to as breakthrough cases. Remember, no vaccine is 100% effective in all people. And that's because every person has their own unique immune system. Yes, most human beings will respond well to a vaccination, but there will always be a small percentage of people who just don't respond to a vaccine, who respond not as well as others to the vaccine. These people are more susceptible to coming down with the disease that the vaccine is intended to prevent. The good news is that the number of breakthrough cases of COVID-19 in vaccinated people, fully vaccinated people in our country and around the world, is currently estimated to be 1%. So right now, for people who are diagnosed with COVID-19, only 1% of them are fully vaccinated. That's a really important thing to know. We're going to switch gears now and spend a couple of minutes talking about how vaccines work. Vaccines can be deposited both into our bodies and on the tissue of our bodies. You've probably had more experience with the injectable kind of vaccine, like the SARS-CoV-2 vaccines. These injectable vaccines can be deposited into the muscle. Some of them are deposited subcutaneously. That's the space that is located below the skin. But there are other vaccines that are deposited onto the tissue of the nose and the mouth. For example, you've probably heard of the intranasal influenza vaccine. That one gets sprayed up your nose. I mentioned the polio vaccine earlier. There is an injectable form of the polio vaccine that we use in young children and infants. But there's also an intraoral version of the polio vaccine. You may have heard of that one. The important thing is that the vaccine gets deposited in the place where it's going to produce the most effective immune response. Remember, the causative agent that's inside every vaccine, whether in whole or in part, that is the antigen of the vaccine. The antigen, which is the thing that can stimulate an immune reaction. The antigens in the vaccine are deposited somewhere that they're going to mount the best immune response. Those antigens are first going to trigger an innate immune response, the first line of our immune system. The innate immune response is going to be triggered by the vaccine antigen within minutes of exposure, minutes to hours across all vaccines. And the innate immune system is going to do two things. First of all, it's going to quickly destroy that foreign material, but it's going to hold on to a little bit of it in order to activate the other half of our immune system, which is the adaptive immune system. Cells of the innate immune system are going to present the antigen to cells that belong to the adaptive immune system. And it's those other cells that are responsible for producing antibodies and for activating immune memory. Part of why vaccination is so important is because it creates within our immune system a memory of the pathogen, so that later on in life, if we get exposed, we will mount an immune response more quickly. We will produce antibodies more quickly and hopefully prevent disease. So, vaccination triggers an immune response by our immune system, by both parts of our immune system. The innate part, that's the first line of defense, and the adaptive part, that's the part that's producing antibodies and memory. We want antibodies produced because antibodies recognize and bind to pathogens and foreign materials and mark them for destruction. The immune memory is critical too, because that's going to allow us to be protected across time. Now, one of the things that can be confusing about vaccination is this concept of boostering vaccines. There's been a lot of talk in the media about whether or not people really need to get both injections of the Pfizer or Moderna vaccine, because both of those vaccines require 2 shots a few weeks apart. The first shot, most people go and get without any issue, but some people are hesitant to get the second shot or the booster. Now let's talk about why we booster vaccines. When we originally get vaccinated against a pathogen, it's unusual to only receive one shot. It does happen. For example, the Johnson & Johnson vaccine only requires 1 shot. Most vaccines require 2 or even 3 shots in that initial vaccination protocol. And sometimes we need to booster the vaccine years later. The reason that we booster vaccines is because it produces the most effective immune response across time. Lasting immunity comes from booster shots. There are 3 things that a booster shot does for us, and I want us to be familiar with this list. Number 1, boostering a vaccine is going to help our body produce more antibodies. That's very important. Number 2, those antibodies are going to be better at what they do. They're going to have a higher binding affinity. In other words, they will be better able to find and bind to the pathogen and mark it for destruction. And number 3, the memory of the pathogen will be improved so that across time, our immune system will be able to recognize and respond to that pathogen more quickly if we get exposed again. On this slide, you're looking at a very simple graph that compares the days after vaccination or antigen exposure on the x-axis with the quantity of antibody produced on the y-axis. You can see that at day 0, the initial vaccination was given. Now, you don't respond to a vaccine immediately. It takes about 2 weeks before you get your maximum response. And if we follow the graph up to about 14 days, you can see there's a nice peak here. If we take that peak and we go over to the x-axis, we can see some level of antibody is produced by that first dose of vaccine. That's great. The problem is that antibody, that quantity of antibody doesn't last. It starts to drop off. Now, by 21 days, by 3 weeks, we're down at a trough. There's still antibody, right? If I trace this over to the y-axis, this person still has antibody circulating, but not nearly as much as they did a week ago. This is the prime time for the booster, when the antibody levels have dropped down considerably, but the person still has some antibody. If you booster at that point, look what happens. Within the next 2 weeks, you're going to mount an even better immune response. You're going to have a much higher quantity of antibody produced, and even after that antibody drops off, it's going to be high. If I trace this plateau over, I've reached that initial peak in terms of antibody production. Boostering vaccines is critically important. Again, not all vaccines require a booster, but many of them do. And the booster is necessary for the vaccine to be as effective as possible against the pathogen. The next thing we're going to discuss is adverse reactions to vaccines. Many of the people who are hesitant to be vaccinated against SARS-CoV-2 are nervous about side effects. You've probably heard that for the RNA vaccines, the Pfizer and Moderna vaccines, many people are reporting that the first shot isn't that bad, but the second shot kind of knocks them down a little bit for a day or 2. People have reported things like fever and headache, muscle aches, terrible fatigue, malaise, just feeling bad all over. The good news is that that bad feeling that often comes from the booster only lasts about a day in most people. Adverse reactions like those to vaccines are not uncommon. But the good news is that they are not usually very serious. Like I said, it only takes a day or so for the bad feelings from the booster shot of the RNA vaccines to go away. That's why most people are willing to go through that second important booster. Most adverse reactions to vaccines are not serious. That's a really important thing to know. The government collects data about adverse vaccine reactions and groups them into one of three categories. There's what we call the common adverse reactions, the less common, and the rare and severe. In the first group, the common reactions, we expect to see these in about 1 out of 4 people who are vaccinated. And again, this is things like pain and swelling and redness at the injection site if the vaccine is injected, muscle discomfort, fever sometimes, fatigue, malaise, just feeling poorly. These are considered common reactions. And again, about 1 in 4. All of these reactions are due to the immune system becoming activated by the vaccine. It's your immune system that produces fever. It's your immune system that produces inflammation. That's the redness and swelling and pain. All of these things are a sign that the immune system is functioning. It has responded. Now, it's important to note that in people who don't experience these common reactions, that does not mean that their immune system isn't working. It just means that they are not as sensitive to the effects that other people feel. Now, for the less common reactions, we're talking about 1 in about 15,000 vaccinations. Generally speaking, these are cases where the fever becomes high. And by high, I mean above 102 Fahrenheit. In some people, particularly young children, a high fever like that can trigger a seizure. Fever seizures, thank goodness, are not particularly dangerous. Most children will come out of a seizure very quickly. And once they have recovered from whatever brought on the high fever, they will not have another seizure. You can imagine, though, if you are the child of the parent, of a child or an infant who has just been vaccinated and then develops a high fever and has a seizure, that can be very, very upsetting. Most parents will bring their baby to the emergency room. They are terrified. They don't know what's happening. Once again, though, this is an immune response to the vaccine. Everybody is individualized in terms of their immune system. And in some people, vaccination not only triggers fever, but it triggers a high fever. And it's that high fever that can sometimes bring on a seizure. So, less common reactions, about 1 in 15,000. Finally, we have the rare and severe category. This is reactions that occur in 1 out of about 1 million vaccinations. These are severe allergic reactions, ongoing seizures, and even death. Yes, people do die sometimes after being vaccinated. By severe allergic reaction, I mean anaphylaxis. That's the kind of immune reaction where the person's throat closes up, they can't breathe, and if they don't receive treatment quickly, they will die. Ongoing seizures means that these people develop high fever, they have a seizure, but that seizure then produces changes in the brain which continue, and they continue to have seizures. And finally, some people will die after a vaccination. These rare and severe effects are also due to the immune system. In some people, the immune system reacts very badly to vaccines. It reacts in some cases by killing the person. Luckily, these are very rare. Remember, 1 in a million. It's interesting to note that the worst of the side effects from the SARS-CoV-2 vaccines, again, death, has occurred in many fewer than 1 in a million vaccinated people. We won't know all of the numbers of side effects or adverse reactions to our SARS-CoV-2 vaccines. We won't know those numbers for a couple of years now, until everyone who wants a vaccine gets a vaccine. But right now, we have no indication that these vaccines are any more dangerous than any other vaccine that's in use